Okay, hello everyone. In this video, I'm going to talk about memory stage units of y86 sequential processor implementation. So let's get started. So here we have units units of memory stages here, and main components is data memory, and we have some control modules. And the basic pattern is similar to other units we implemented before. Okay, so we have main components of each unit, each stage, and then to select correct control signal and data signal, there are control modules, mostly combinational logics, which selects multiple input data and some um, instruction code or some necessary information, and then selects correct control signal or generates control signal or selects correct input data. Okay, let's see one by one. So for data unit, yeah, it's simple. It does read or write data to or from RAM. Okay, so note that this is RAM, which can read and write. But note that in fetch unit, we can use either ROM or RAM, because once your machine code is loaded to the instruction memory, then we never modify or update, right? So it can, the instruction memory can be ROM, but data memory must be RAM. Read and write function should be there. So it takes three inputs, two data inputs and two control signals. So for data input, which is address line and data line. And then for control signal, it takes read and write signal. And then if it is a read signal, so if it is the control signal is read, then it will output the value. Okay. So, and also it has one extra control signal outgoing from data memory, but I'm going to talk about it maybe last tutorial. Okay. All right, then let's see each control modules, how it selects or how it generates data signal, data line, or data inputs or control signals. Okay. First is read memory and read write module. Okay, you can implement these two logic in a same module, or you can make it separately. Okay. So each module generates read or write control signal based on instruction code, I code. Okay, it goes to both RAM read and mem read and mem write. And then also for data address, mem address and mem data module selects correct address line and data line. Okay, so for address line can come from value E generated by execution unit, or it can be from register file value A. Okay, so it depends on which instruction we are fetching and executing. So we can select correct address line, either value E or value A. Okay, again based on instruction code. Okay, so then for data line, so we have two possible data line coming from value A or value P. Okay? Value A is from register file, and value P is from instruction machine code itself, a constant value. Okay. Oh, sorry, not from the machine code. It is computed in the fetch unit. Okay. And actually, val p means the one of the candidates of next PC value. Yeah, I believe you remember that, and we talk about it in the fetch unit. Okay, good. So then let's see how. Let's see the actual selection logic for each 4 control modules. Okay, like we did in the previous tutorial, I made a one table for four control modules, and each column is associated with one control module, like mem read, mem write, and mem address, and mem data. Okay, so you can so fill out this table for each instruction, and for each module has a possible selection. Like first, mem read module can generate control signal 0 or 1 bit signal, and 1 means read signal, and 0 means no read. And mem write module, same, generates 1 bit signal, and 1 means write, 0 means no write. And for memory address module, yeah, it selects either value E or value A, and memory data module selects either val A or val P. Okay, so let me take one example. I'm going to take a couple of examples, not everyone, and then you can fill out the other remaining parts. Okay. Which one is good example? Let me see. Maybe RM move. Yeah, some memory related instruction will be useful. Okay. Let's use this one as an example. Okay. So like we practiced with this instruction format. So to understand basic flow of this execution of R and move instruction, we can write down something like equation, something like mathematical notation, yeah, since it is moving data from register RA, so register RA, read register RA, and then move this value to the memory memory M, address is D plus register value R B. Okay, but let me rewrite this part, maybe upper side, so then you see more clearly. So RB data comes from register RA. Okay, so let me repeat this instruction. Let me read this instruction again. Okay, 1 second, please. Let me erase some unnecessary part here. Okay, so let me read this line again, once again. So first, so we read RA register from the register file, and then move the written data to the memory address D plus value of RB register. Okay, so this is the detailed information, and then based on this, we can decide this the signal selection. So since we are practice with RM move instruction, so for memory read signal, so what we are doing is we are going to write some data to the memory, not reading something. So it will be 0. Okay, and then yeah, since we write something to the memory, it should be 1. Okay, and then address. So then we should know where address comes from. Okay, here address is this one, right? D plus R, register value of RB, but it should be computed, right? So then these two value, D, which is from machine code, and register value RB from register file, should be computed in by execution unit. Okay, then output of execution unit is val E, right? So we should select val E as a address. Val E. Okay, good. And then where is the data? So data is in the memory side. Oh, sorry. Yeah, memory side. So so this input, this module, mem data module, selects data to be written to the memory. But in this instruction, we don't want to write anything. Okay. So we want to. Oh, sorry. My bad. We want to read. We want to write value which is from the register file. Okay. So here. So this, when we read register value of RA, then value will be in the wire val A. Okay. So we should select val A for RM move instruction. Okay. We are done. Okay, let's practice with MR move instruction, which is the reverse way of data flow. Okay, then let me change. Where is it? Let me erase the instruction, erase something, and then here, and then write the equation of MR move instruction. So since it is data from memory to register, so we can write this way. First, we read data from memory. So from memory, and what is address? Address is D plus register value of what? RB. And then this value goes to register what? RA. Okay. Then let's fill up the row of MR move instruction. Okay. So is it read or write? This is reading a memory, right? So we read memory here. Okay, then it should be 1. And we don't write anything to memory, so it should be 0. And then for address selection, where is address? So address comes from this equation, and this equation should be computed. So these values should go to the execution unit and then computed and then output through value E. Okay, so it should be value E as well. Okay, and then what about data? Where is the data? Actually, so this module actually selects data which will be written to the memory, but in this case, we don't write anything. So here, we don't care. So as long as you generate write signal for write like 0, which means whatever data, the data line, whatever data in the data line is going to the data memory, it won't be written because we that is controlled by this control signal. Okay, yeah, simple. So once you finish this work, then you will have something like this. Okay, dada. Yeah, again, we don't implement, from control move to pop. Yeah, but just I fill out this. And then, yeah, so then you can implement and then integrate data unit, memory stage unit to the your existing circuit and then play with it. But here I have two more things to talk about. Okay, so since you implemented execution unit, you may have some issue with timing. Okay, and I mentioned about this timing in the demo video of execution unit very roughly. Okay, so if you have this issue, then you are good. You are on the right track, and it's time to talk about that. Okay, let me give you example why we should consider timing. Okay, because each unit must start their execution at a correct timing or correct cycle. Otherwise, the unit will read some not ready value or some random value or trash value or not correct value, and then output some, again, um, random value or no meaningful the output, and then that will affect next unit, and then your logic will be messed up. Okay, so for example, let me just for simple example, so here, so it takes two data, and this is ALU and control signal, which operation we will do, and then it outputs computed value. But think about it, when these two data is ready. Okay, so there are candidates of input data, and you should know which candidate the longest cycle to get uh, the one of this value. Okay, so we should know the longest time you should wait these four values. For example, like one is like this data, it will be ready after 2 cycles, for example, and this another candidate is ready at cycle 3, and this is ready at cycle 4, and last candidate is ready at cycle 5. Then when does this ALU can start its execution, which cycle? Since we want to make this timing simple. Okay, to be conservative, this ALU should wait until cycle 5. Okay, then we guarantee all of the inputs are ready, or these two inputs are ready, and then we can this ALU module can start its computation. So in this example, this ALU can start at cycle 6. Okay, because the last data, like one data, this one is ready at cycle 5. We cannot start cycle 5, we can start cycle 6. Okay, so this is the one typical example why you should consider starting time start cycle of each unit. Okay, this issue happens for every stages, right? Fetch unit has also same issue, and register file like a write back stage, and execution unit like this example, and also data memory stage or memory stage has similar issue. Again, last stage, PC update stage has this time issue. Okay, when to read data or when to output the data. Okay, so that's why I'm drawing this topic, timing diagram. Okay, so then whenever you integrate new module, you should have timing diagram. Okay, and then you can figure out which timing each module can start. Okay, so here I made have completed timing diagram. Okay, so and I listed out some output values of each unit. Okay, so maybe first, how many? 6 inputs from fetch unit, and then second 2 is from decoding unit, and then next is from execution unit, and next is from memory stage, and next is PC update unit. Okay, so then for each cycle, on top of this diagram, yeah, we have a timing clock signal, and then you should draw from which cycle to which cycle I code wire or line will store the valid data, here yellow color. Okay, so in my design, it is valid at first cycle 0, and then it will be available at some cycle. I didn't draw when is finished until when this I code or other values are available. Okay, yeah, I intentionally didn't draw so that you figured out your own timing. Okay, so for example, if it is available at cycle until cycle 11, which means your next new cycle for the next instruction will start at 12th cycle. Okay, this whole thing will be repeat after 12th cycle. Yeah, that's what you have to figure out. Okay, let me erase something. Okay, so here I just drew for the fetch unit. Okay, see here. So since the I code and I function is stored in the first byte of the machine code, so it is available at the first cycle, right? Once we read 1 byte at the first cycle, then both I code and I fun is available. And then it is keep having same value until the end of the last cycle of this instruction execution. And RB and RA register values are stored in the second byte of the instruction, right? So it will be available at the next cycle, cycle 1. Okay, and also, so val p can be the val p can be calculated after we fetch I code, right? So since once we know I code, then we know the size of the current instruction, so we can calculate it. So after first cycle, again, at the second cycle, we can have valid val-p data. Okay, and then after we read remaining 4 bytes of the instruction, then we have completed value C. Okay, here. So that my instruction memory can read 1 byte at a time, 1 byte with one address. So after one cycle, we read first byte of val_c, and then next cycle we read second byte of val_c, and then next cycle we read third byte of the val_c, and then next cycle we read fourth byte of the val_c, and then finally we have a valid data. Okay. Yeah. Then we consider, okay, fetch unit stage is finished from, yeah, so at cycle 5, okay, until here. So then from cycle 0 to cycle 5, actually fetch unit worked. Okay, and the next, yeah, there will maybe it could be decoding unit, or decoding unit can be overlapped with fetch unit. Okay, as long as all the input to the decoding stage is ready, then it can start. Okay, so the decoding unit just needs RA and I code and RA and RB values. Okay, then when as long as these 3 values are ready, then decoding stage can start. Okay, which means decoding unit can start cycle 2, right? Because at cycle 1, 3 values are ready. Okay, so from here to, and then it takes on to read values, it takes 1 cycle. So decoding stage will be just 1 cycle from cycle 2 decoding stage. Yeah. But what about execution unit? Execution unit need what's the inputs of execution unit? Yeah, we should know that to determine timing of execution unit. Yeah, maybe val_c is one candidate of input to the execution unit, and val_a and val_b also can be uh, data input to the execution unit. Okay, so after we read all of these candidates input, execution unit can start. What is the longest one? Actually, value C. Okay, value A and value B will be available earlier than value C, so we can start execution unit at cycle 6. Okay, and so on. Okay, I just give you this timing diagram of my design until execution unit. Okay, you can like based on this understanding, you can draw your own timing diagram, and then um, you can control when to start each unit. Okay, so here I have a tip to implement that timing. So you can simply use counter. Okay, so at a certain timing, you can enable all the control signal inside each unit. And then if, for example, if it is execution unit, you can start outputting the correct computed data. Okay, that is one tip or one suggestion how you implement or how you control this timing of execution. Okay, yeah, this is it about timing diagram. And another thing is data memory file, or the yeah. Why I'm talking about it? Because we have two different memory, one for instruction memory, the other for data memory. But until before you implement fetch, decode, execution stage, we didn't play with data memory, so we didn't generate. Maybe you may not generate a memory file for data, right? um, so we can reorganize output binary file of y86 assembler. Okay, in this output binary, it contains both machine code and data, right? So when you write test assembly code for data memory stage, then you probably write the data information, okay, which address, which value, okay, using directives dot long. Then you can store machine code part in the, you can generate two memory file, one for instruction memory with only machine code, and the other memory file for data. You can just store, reorganize data part and then create a separate file and then use that file to load your data into the data memory. Yeah, but be careful when you reorganize data memory file for data. Okay, I'm not giving you super detail. Okay, I'm giving you one example in the demo video. Okay, you can watch for some more detail. Yeah, once you watch my demo video, then you figure out how to reorganize the output binary file. Okay, good. Okay, in the next video, I'm going to demonstrate memory stage with a new test program. Okay, bye. Thank you.